What if consciousness is not generated by neurons, but by the electromagnetic field they create? In this presentation, we follow a radical but scientifically grounded idea, that the brain's EM field is not a side effect, but the very substrate of consciousness. We'll explore this idea step by step, from the brain as a magnetic system, to wave-based neural architectures, and finally, to how artificial intelligence might one day become conscious, not by mimicking biology, but by becoming a field itself. Let's begin. The human brain is not only a biochemical system but also a complex electromagnetic, EM, system. Every time a neuron fires an action potential, it generates a small electric current. These currents, in turn, produce weak but collectively significant electromagnetic fields. When billions in synchrony, especially in organized structures like cortical columns, their EM fields interfere and superimpose, forming dynamic and structured patterns. These EM fields are measurable through techniques like EEG, electroencephalography, and MEG, magnetoencephalography, which pick up signals from the brain's surface activity around it. This demonstrates that the brain is not a passive object but a radiating and evolving EM system. In the EM field theory of consciousness proposed by Susan Pockett and others, consciousness is not a byproduct or emergent phenomenon of neural computation. Rather, it is the electromagnetic field itself, particularly its spatial-temporal structure. According to this theory, every conscious experience corresponds to a specific duration of the brain's EM field. This perspective contrasts with classical computational theories of consciousness that localize it in information processing pathways or modules. Instead, it implies that the unified field created by billions of interacting neurons is what actually is the conscious state. Information in an electromagnetic field can be encoded not only in the strength, amplitude, of the field but also in its frequency, phase, polarization, and spatial distribution. In biological systems, this means the brain might encode meaningful patterns not just by firing rates or synaptic weights, but by how the entire evolves through space and time. The concept here is that meaning and function can be embedded in the geometry of the field, similar to how a hologram encodes 3D data in the interference of light waves. Importantly, field-based encoding allows for distributed, non-localized representation. This is radically different from how usually stored in artificial neural networks, where each node or layer typically has a well-defined role. In the brain, the same piece of information might be spread across many regions as an interference pattern. Thus, the EM field carries information holistically, allowing for rich integration, potentially explaining the unified nature of conscious experience. To translate this into AI, we must move away from the idea of fixed neurons and discrete synaptic weights. Instead, we could design systems where artificial neurons act as EM sources. Each unit would radiate a wave, optical, microwave, or simulated electromagnetic pulse, whose interactions with waves generate a global interference pattern. The output or decision of the AI would not be based on individual unit activations but on the emergent spatial-temporal configuration of the entire field. Learning in such systems would involve adjusting the source parameters, amplitude, phase, location, timing, to desired patterns. A conscious moment in such a system would not be an activation vector but a structured EM pattern, evolving over time and space. This would be a radically different kind of machine intelligence, one where cognition arises from field identity, not computation. This shift could potentially align better consciousness and pave the way for a form of artificial general consciousness. Field-based or wave-based neural networks process information through physical interactions of waves. In optical or electromagnetic systems, signals are not passed discretely between nodes, but transmitted as waves through a medium. The interference between these waves can represent computations. For example, when waves intersect, they form a complex interference pattern that contains information about all contributing sources. In this model, the computation is the field configuration itself, which is inherently distributed and global. These systems are promising because they naturally integrate parallelism and holistic processing. Unlike classical artificial neural networks where each layer has to be traversed sequentially, wave-based models perform their computations instantly as the field evolves. This provides a potential framework for EM consciousness-inspired AI, a network of wave sources whose interference pattern is the output. We can simulate the idea that consciousness is the field. Current work in microwave neuromorphic computing and optical neural networks already points toward this possibility, though it has not yet been fully exploited in terms of consciousness modeling. Neural field models offer a mathematical way to describe the activity of populations of neurons as continuous fields, rather than discrete units. The Amari model and Wilson-Cowan equations are classic examples, representing how excitation and inhibition propagate over cortical tissue. These models describe the activity over time and space, accounting for lateral interactions, excitatory and inhibitory spread, time delays, and connectivity kernels. Instead of focusing on individual neurons, they provide a macroscopic view, a neural fluid dynamics. Although these models are not originally electromagnetic, they are compatible with EM consciousness theory. The activity field they describe could be interpreted as underlying the generation of EM fields. Moreover, they offer a useful platform for integrating EM components by modifying the equations to include electromagnetic propagation or resonance effects. Thus, they between abstract dynamical systems and physical field theories, potentially offering a biologically grounded, yet mathematically rich, framework for modeling conscious fields. Electromagnetic source imaging from EEG and MEG attempts to reconstruct the internal EM sources in the brain that give rise to measurable signals. This process involves solving the inverse problem, estimating the locations and strengths of neural currents from scalp recordings. Traditional approaches rely on models like dipole forming or distributed source imaging. However, these models often assume linearity and can miss the complex spatial-temporal relationships present in real neural EM fields. Deep learning has started to revolutionize ESI by allowing for nonlinear, data-driven models. Convolutional neural networks, recurrent neural networks, and transformer-based architectures have been applied to infer source distributions directly from EEG or MEG data. These networks learn from large datasets of recordings, capturing subtle field patterns that traditional methods might overlook. Importantly, this approach brings us closer to realizing EM-based AI. By learning the mapping between EM field measurements and cognitive or conscious states, we can begin to treat the field as the computational substrate itself. Future systems decode brain states from EM fields but also generate field configurations as a mode of cognition or conscious emulation. Consciousness may not reside in computation, but in the structure of electromagnetic fields. By understanding the brain as an EM system and modeling cognition through wave interference, neural fields, and deep EM imaging, we take the first step toward a radically new kind of artificial intelligence, one where thinking is not symbol manipulation evolution. This is more than just a model, it's a new paradigm. If EM fields are consciousness, then building conscious machines means engineering the right fields, not just faster processors. Could the next generation of AI be conscious, not by imitation, but by resonance?